kind of presentation for these volume problems. So here in this problem it says we have a circular, or a solid with a circular base with radius 1 and parallel cross sections perpendicular to the base have are equilateral triangles, and we're asked to find the volume for that solid. So if I kind of just sketch a little bit of a picture here. So there's my circular base, right? Now, if I take some cross section perpendicular, that's like the base of my triangle, of my equilateral triangle. That's what it's saying. So if I draw that equilateral triangle, I have something like that, right? So my area function is going to be the area of that triangle. Does that feel okay? Now, it told me the cross section, right? So what I want to do here is, since it's a circle with radius 1, I know it looks like this, right? First thing I'm going to do is decide whether I'm going to be integrating with respect to y or with respect to x. And it turns out in this problem it doesn't really matter, right? Because if I think about the base of my, like this thing being a circle centered at the origin, whether I slice perpendicular to the y-axis or perpendicular to the x-axis, I'm going to get the same answer. Now the problem says it doesn't imply that anything has to do perpendicular to either axis, so I'm just going to pick one. I'm going to pick doing this to the x-axis because it feels more natural. Does that feel okay? So if I do that, this spot is just some x, and that distance there is going to represent a y, right? Everybody feel okay there? So if I rewrite this equation in terms of y, I have that. Is that okay? And my base then is going to be 2y. You guys okay with that? And because this base of my triangle is a distance, what am I going to do with that, plus or minus? Just going to make it positive, right? Is that okay? Now, to get the area for this triangle, my typical area formula I'd use is 1/2 base times height, right? So I'm going to have to figure out the height of that triangle. Now, what I observe here, if I take this and redraw this, for a moment. that this is a 30, 60, 90 triangle, right? I remember that the side lengths of a 30, 60, 90 triangle exist in the ratio 1, root 3, and 2. So if this side is y, oh my goodness, guys, that's not right. Hold on a second. This is the root 3 a side. Yikes, right? Because that's longer than 1. That should be opposite to 60. My apologies. So remember that this side is my y. So this side should be y square root 3. Or I could write that as square root 3 times square root 1 minus x squared. So far, so good. So my area function then, if it's 1/2 base times height, the base is 2, 1 minus, or square root 1 minus x squared. And then my height is square root 3 times 1 minus square root x squared, which I'm super excited about. Because what's going to happen? Yeah, when I multiply these two guys together, those square roots cancel, and boy, that makes the integration a whole heap easier, right? So what are we left with is just square root 3 times 1 minus x squared. So now we have everything we need to integrate this. So my integral is going to go from, if I'm going along the x-axis, I'm going from -1 to 1. And then it's my area function dx. Does that feel okay with the setup? Because the volume integral is always just the integral of the area function dx. And the problem told us the area formula that we needed. It told us that the shape was equilateral triangle. It told us how to write the area function. Now, was there some work in sorting out the side lengths to plug into the formula? Sure. Is the equilateral triangle the worst cross-sectional shape you're going to see? Yes, typically. But that's part of the reason why I chose this one, is to kind of give you a worst-case example. Why is it typically the worst one? Because you have to find the height. More often than not, it's just not like a simple whatever. You have to kind of work for that a little bit. Okay, so continuing on then. I noticed that this circle, when I look at this solid is going to be symmetric, where this half of the solid would be the same as that half of the solid, right? You guys okay there? So when I have that situation, when it's symmetric like that about the origin, I can do that same trick. And again, it's not like a massive trick, but, you know, like if it saves me from having to do some extra, if I can plug in a 0 instead of another number, I'd rather have that. Does that feel okay with everybody? All right, so let's do our antiderivative. So the 2 square root 3 is going to come out front. The antiderivative of 1 is just x, and the antiderivative of x squared, x cubed over 3, and we'll evaluate from 0 to 1. So we're left with 2 root 3 times 2/3, or 4 root 3 over 3. Feel okay there? I know, that's hard. It is. With that in mind, I have some practice along the same line. We're going to pass. Let me just drop this in. Can you just set those on top of the file cabinet for me, Jack? Thank you. Perfect. All right. So let's do 1 or 2 of these guys, and then we'll do a little bit of talk a little bit about shells, and that'll probably be our day. Sound good? Mm-hmm. Not like at the ocean, but as a second, or an eggshell. All right, so number 1 says, let R be the region in the first quadrant bounded by the graphs of y equals x cubed and y equals 4x as shown in the figure above. The region R is the base of a solid. For the solid, each cross-section perpendicular to the y-axis is a square. What is the volume of the solid? So immediately I know my area function is a square, right? It tells me in the problem. I just have to figure out how do I represent S. Everybody's okay with that? So it says that my cross sections are perpendicular to the y-axis. So this S is a representative side length for one of these possible cross sections, right? So if I think about S as the distance from the point x2, y2 to the point x1, y1, because x is horizontal, it's going to just be the distance of x1 minus x2. Everybody agree with that? Oh, no problem.
In case you were looking for something to do yesterday.
So far, so good? All right. So what I need to do now is I need to represent my function, or this point, x1 and x2, in terms of y's, because I know for integrating, or if the cross sections are perpendicular to the y-axis, that's what I want to be integrating along, right? because I'm going to be doing dy's. I guess I should say. So in y1, as per the way I've labeled that, is x cubed, right? How could I tell which curve was y equals x cubed and which one is y equals 4x? The straight line is the linear one and the curved one is the polynomial one, or the cubic one anyway. So x1 is just going to be the cube root of y1, right? And y2 would be equal to 4x2. So if I just divide by 4, x2 is y2 over 4. So my s should be the cube root of y minus y over 4. Does everybody feel okay there? So my volume is going to be the integral, since we're going along the y-axis, we're starting at 0 and we're ending at 8, of the cube root of y minus, bless you, y over 4 dy. And how am I going to find the value of this integral? I'm just typing this stuff into my calculator and pressing enter. If you have your calculator out and with you, I invite you to kind of do the same thing just to double check that you are getting the same result that I'm going to get. So again, we're doing math, scrolling down to the command 9, which is fnint. And then we can just, one thing. Forgot the squared, right? It's s squared. So there's a squared right there. So to do y, or the cube root of y, I'm just going to do like to the 1/3. And again, it doesn't matter on your calculator if you're calling the variable x or y or, you know, whatever it is. I just type x's into my calculator. So that's all I'm typing in. I press enter and I wait a second or two, or 3 or 4. And there's my answer. It looks like this should be B. Does that feel okay as to what we did there? I like these ones. Now, they're hard to picture in your head what the shape is going to look like, but I don't care. What I care about is like that it's told me in the problem the area shape. So all I need to do is figure out how to represent the dimensions of that shape in terms of the functions, like so it has x's and y's in it, so I can integrate it. I'm going to scroll here a little bit. Let's just look here at what I have here. I think I printed the wrong things here. All right, let's do this one, 10. I thought all of these were going to be, it told us what it was, but apparently some of them are just generic washer and disk ones. 10 says, let R be the region in the first quadrant bounded by the graphs y equals 4 cosine pi x over 4 and y equals x minus 2 quantity squared, as shown in the figure above. The region R is the base of a solid. For the solid, each cross-sectional area perpendicular to the x-axis, that tells me this is a dx problem, is an isosceles right triangle with leg in region R. So normally a triangle as length or as area base times height, right? But if it's an isosceles right triangle, the base and the height are just the same thing. Everybody's okay there? So this is really just going to be 1/2 like leg squared. So if I said I'm going to draw a typical leg here. So it says we're drawing perpendicular to the x-axis. So that's like my L. If this point is x1, y1, and this point is x2, y2, then L is just y2 minus y1. Everybody feel okay as to how I came up with that? Now I know that y1, or this curve, is that the quadratic one or the cosine one? Quadratic one, I can tell because it's opening up, and that's a positive leading coefficient on that quadratic, so that's got to be the quadratic one, because the other one is concave down, which is not what I'm looking for, right? So y1 is just x minus 2 squared. So y2 is just the 4 cosine yada yada yada. So my volume is just going to be the integral, since we're going along the x-axis, from 0 to 2, 1/2, and then we have y2, which is my cosine function, minus y1, which is my quadratic function, squared, dx. And then it's just calculator time, right? This one was much easier because I was integrating with respect to x, so I didn't have to solve my equations in terms of y to plug them in for the length for one of these sides or whatever. And again, if it's a calculator problem, I am not doing anything to make this easier. I'm going to let it be as hard as it possibly can. Let the calculator deal with it. It'll sort it out on its own. I don't need to worry my pretty little head about it. I'm just going to type it in exactly like it looks. The one thing I would be careful about, though, is the mode of my calculator. Since I have a trig function involved, I know I need to be careful about that. What mode is my calculator always in AP Calculus? Radians. So I want to make sure that's the case. It is. So there I get 1775-ish. That looks like my answer for A. What do you guys think on these? They're usually not too bad because they give you the formula to use. All you got to do is like figure out the dimensions in terms of the function, and it's smooth sailing. Is everybody okay with this? A couple of examples. It's a common AP presentation. You probably wouldn't see more than one or two of them on an exam, though. You know, like there's not like there's going to be a million of these. All right. So the next topic we're going to talk a little bit about here before we have to go in 10 minutes. So we'll just start talking about this. We'll finish it next time. Is this idea of instead of taking slices of our solid to try to find the volume, is to like unpeel it. So like we're going to take a layer off, calculate the surface area for that layer, and multiply by the thickness of that shell that we've peeled off. That's like my dx is going to be like the thickness of that shell. And we'll add up all those peels that I've peeled off. And the volume of all those peels added together is going to be the same as the volume of our figure. Now, this is harder to imagine, and I think is less useful than the discs and washers that we've been doing until you get to one example. So say we have this function x squared, or I'm sorry, 2x squared minus x cubed, and it's bounded by the x-axis, so it's this picture here, and we rotate that around the y-axis. So it's going to be like, kind of like a swimming pool shape, right, where it's like a pond or something, right? Everybody's kind of see that? Now, if we try to do a washer on this, here's the problem, is that my inner radius and my outer radius are the same function. Oh, rats. That's a problem, right? Now, you could be clever and come up with a way to get around that. Or, if you're doing a shell, this is not a problem. This falls perfectly into shell territory, which is good for us. Is that, you see where trying to do a washer on here is going to be a problem? Because this is the same y having two different x's. Rut-row-raggy. That's a tricky wicket that we've just stumbled into. You know, like that's going to be rough. Now, the alternative is to think about this as like unpeeling this thing. Or sometimes, like if you think about those like Russian nesting dolls, it's kind of the same idea where you just like take a layer off, take a layer off, take a layer off, take a layer off. So the idea is we're going to be building these hollow cylinders out of our solid. So each cylinder that we pull off is like a layer. You know, that's like one wrapping around. And the point of using a cylinder is when you unfold it, the cross section is a rectangle. Well, it would be a cuboid, but like, you know, when you unfold it, a cylinder, it's a rectangle. If you don't have a top and bottom on it, you know, if it's like a open cylinder like this, you got like a box with a really thin box, which is great because the volume or the areas of those are easy to calculate. Rectangles, the volumes of rectangles are really easy to calculate. This sounds pretty good. So basically, when we do these slices, the volume is going to be for one of these shells is going to be like 2 pi r h times the change in r, the thickness. Blah, 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 blah. All right, so like if this is our solid, this is a picture imagining like doing the shells to it, right? So this is like what our shells kind of look like, and we take infinitely many of them, and you see like, you kind of visualize what's going on. I know this is much harder to visualize, but it's okay. Like when we draw the two-dimensional picture, we'll talk through like how to get the measurements from the two-dimensional picture that you need to do the area or to do the integral formula. So what this boils down to is it's basically the integral becomes 2 pi x f of x dx. So the f of x dx, or the f of x, is like the height of our rectangles, and the x is like the, well, I guess it's the 2 pi, the x is like the radius, right, of the cylinder. So the bottom is like the circumference of that circle, right? Because if you take this rectangle and you build it into a circle and connect it, you have that cylinder again. So that bottom edge is the circumference of that circle. All right, so let's go ahead and build out this guy here. So if I take one typical shell, that's what we have here, right, that I've drawn in. This x is the radius for the shell, and the f of x is like the height of the shell. So my volume is just going to be the integral from, we're going to be integrating along the radius, so we're going from 0 to 2. And then just 2 pi x f of x dx. Now to integrate this, let's pull the 2 pi out front, and we'll distribute the x through. So now we just need to do the antiderivative of that. So it's going to be 2x to the 4th over 4 minus x to the 5th over 5 from 0 to 2. And you just kind of grind from there, right? Let's do another A. We probably got time to squeeze one more quick one in here. Okay. Use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis. So we're going this way. The region under the curve, the square root of x from 0 to 1. I want to point out to you guys, a shell is a stupid way to do this problem. I would just use a disk, right? Super simple disk problem, but for the sake of argument, let's do it as a shell to show you that being able to choose appropriately is like really helpful. So if our axis of rotation is the x-axis, this is like my radius. That's a y value. And the height of my shell then is going to be like this distance. So again, it's from like the solid part forward. So I know all the points on here are like x comma y squareds. So this distance is x, so this distance must be like 1 minus x. If this distance is y, I shouldn't say y, I should say it's like x comma x squared. Oops. Or square root x, I should say. So if I start putting this together, then I'm going to have the integral. We're going from 0 to 1, 2 pi, and then our radius is y. All right. Are we out of time here? We'll pick this up next time. What I would suggest for you is try a little bit of these guys. We'll do more on this next time. Try some of these 6-3 problems. Try a little bit of the other ones in the packet I gave you just a few minutes ago. We'll take next time a big day of questions, and then we'll just have some time to work on some problems in class doing this. Okay, so come with questions next time. We'll finish up 6-3 and we'll work on problems in class, and that'll be the plan. You guys feel okay?
Mr. Will, do you have any more of those packets that you